All right, let's do another example here, but this is going to be a little bit trickier. I'm going to go ahead and draw my source. Let's say it goes 0 to 10 volts. I'm going to draw my ground. And then what I'm going to do now is I'm going to switch my capacitor and resistor from where they've been this whole time. All right. And I'm going to go ahead and call this a 1 microfarad capacitor, and I'll call this a 1 kilo ohm resistor just to make it simple. And what I'm interested in finding is I want to know what is the voltage at this node, Vx of t. That's what we want to look at. We want to see what does that voltage look like, okay? And so we know what Vc of t looks like. We do know because we know our charging equation, but we need to examine a little bit further to see what Vx of t looks like, okay? So we're going to label that node Vx of t. Let's call this node Vs of t. And let's just go ahead and plot them all. Okay, so what does Vs of t look like? Let's start with that question. Vs being, so there's two nodes in this circuit that we're interested in. We're interested in this node, and we're interested in this node. All right, and so we know Vc of t pretty easily. We can go ahead and use our charging a capacitor equation. Let's say again that our Vc at time t equals 0 is 0 volts. Okay, and so let's just go right back and grab our charging equation again. I'll just go ahead and grab this, copy it, paste it right here. And so we know right off the bat that our RC is tau equals 1 kilo ohm multiplied by 1 microfarad. I did that on purpose because that just gives us 1 millisecond for the time constant. Nice and easy. And so our final value is going to be 10 volts for Vc of t. So then my equation here is just 10 times 1 minus e to the minus t over tau is equal to Vc of t. And so what that tells me again is the Vc of t. It's the voltage across my capacitor, but it doesn't tell me Vx of t, okay? Vx of t is that green node voltage. Vs of t is the pink node voltage. And Vc of t is the difference between the two. So if I were to write an expression here using KVL, I could say that Vs of t minus Vc of t, right, minus the drop across the capacitor, is actually what gives me Vx of t. So if I want to know anything about Vx of t, I need to figure out both Vs of t and Vc of t. Well, I just figured out Vc of t using my charging a capacitor equation. So what does Vs of t look like? Well, it's actually pretty simple. Let me go ahead and draw a little plot here. I'll call this, so let's actually go ahead and make 3 of these because we're interested in 3 different things here. I'll copy this, I'll paste it here, and then I'll paste another one here. So we're interested in 3 things. We're interested in Vs of t. We know Vc of t, and we can plot that. And we're interested in Vx of t. Okay? So again, my question here is, what does Vx of t look like? Basically, let's say that the question asks, plot Vx of t, or sketch Vx of t, or something along those lines. Okay, so Vc of t, we know what that looks like. That's going to look like I'm going to have nothing going on for all the time t equals 0. My voltage source turns on, and it'll ramp up to 10 volts in about 5 tau. Right? That's exactly what my Vc of t is going to look like. Well, what does Vs of t look like? Vs of t is 0, right? Let me pull out my laser pointer. Vs of t is 0, and then at time t equals 0, it pulses high up to 10 volts and just stays there. That's my pulse source. So what it's going to look like is something like this. It's going to be 0, 0, 0, and then at time t equals 0, it pulses right up to 10 volts and then stays there. Okay? And so if I wanted to know what Vx of t looks like, well, from this expression, I know that Vs of t minus Vc of t gives me Vx of t. And so at any given point on this, this graph, I could just take 10 volts, right? That's Vs of t for all time t greater than 0. Basically, I could say Vs of t is equal to 10 volts as long as t is greater than or equal to 0. And so at any given time, I can just take 10 volts minus Vc of t, and that would give me Vx of t so long as t is greater than or equal to 0. Okay, so Vx of t is obviously going to start at 0. And then at time t equals 0, immediately Vs of t jumps up to 10 volts. Vc of t stays at 0. So my difference there would be 10 minus 0, or 10. So Vx of t is going to jump up to 10 volts as well. And then from there, as I increase voltage, let me take out my laser pointer. As I increase voltage, and this stays at 10, my voltages here are decreasing. And so that's what my Vx of t is going to look like. It's 10 volts minus Vc of t, right? And so that's an important concept. I guess I didn't treat this so much as an example problem as I did just to show the concept of what happens to the green node in this circuit, because it's important to note that there's a difference between Vc of t, the voltage across my capacitor here, and the node voltages in the circuit. Vs of t goes straight up to 10. Vc of t, my capacitor voltage, does what any charging capacitor would do in an RC circuit. And Vx of t does this thing where it pulses up, because initially at time t equals 0, the voltage across the capacitor, it doesn't want to change instantaneously. So in order for that voltage to stay at 0 to start, my Vx of t has to jump up to 10 volts with the source, okay? And then from there, this Vx of t node bleeds off back down to 0 as my capacitor charges. And then in the final state, Vx of t is 0, Vs of t is 10, and my capacitor is charged to 10 volts, okay? So this was just another example, another really important concept for charging a capacitor. And in the next slide, I believe I'm going to talk about energy storage. Yep, energy stored in a capacitor. And then we'll get into discharging capacitors and examples for discharging capacitors in later videos.